Welcome to lecture 3, which is going to be about user authentication. I'm Frans Kashuk, and I co-lecture with Nikolai this class. I see a lot of familiar faces from 828 from last semester, and so I guess welcome to the next class. So the topic for today, actually before jumping into the topic today, one logistic issue. We are intending, or we're trying to record these lectures so that you're aware that they're there. We hope to post them. We'll see if we succeed in doing that. But we'll keep you posted on that. But if you ask a question, you might get recorded. If you don't want to be recorded while asking a question, ask the question through the website, and then one of the TAs or Nikolai will ask it for you. Okay? Okay, so the topic for today is user authentication. And that turns out to be a pretty broad, deep, wide topic, and so I'll try to get a cut through it in one lecture so that we at least have something to talk about, but I certainly won't be able to cover every aspect of it. And the reason it's such an important topic is because it's basically the underpinning of many security policies. Typically, many security policies are user-specific. You log into the bank, or I log into my bank. The bank wants to make damn sure that it's actually really Frans Kashuk that is doing this transfer of like $1 million to somewhere else, right? And so the user authentication is a crucial part of most of any policy, and so it's really important to establish who's actually the user that's actually logged in. It has a lot of interesting technical issues. And some of them I will highlight in today's lecture, and some of them you will encounter in lab 2, where you will be programming some aspects of this. User authentication is hard, partially some of the technical issues, but it's also hard because it's the first place where we clearly see security running into convenience. It's possible to make really, really good, strong user authentication that is really damn hard to use, and people just won't use it. And we see that as a theme, through this lecture. And there's one reason that we still have user passwords. Right? User passwords is like an old idea, dates back to the 1960s, but it has been a long-lasting idea because, in many cases, it actually is very convenient to use and can have pretty good security. And so we'll see that showing up in a bunch of places where there's a trade-off between security and ease of use. Another aspect of user authentication is that almost all of you, or everybody basically that uses a computer system, has experience with it. And so it turns out lots of people have lots of opinions about this. And it's a topic of strong opinions in many cases, and some are reflected in all the questions that you asked. In fact, the wide range of questions that you asked, I'm not sure I will be able to cover all the things you asked, but feel free to jump in anywhere where you feel like, this is the question I really wanted to ask. You're not addressing it. Let me ask it. Okay, so before jumping in, let's just remind ourselves what the setting is, where this issue of user security shows up. So Nikolai, talked about last lecture and lecture before about sort of the guard model of security, right? This is like a good overall architecture to design computer systems to be secure. And the basic plan in the guard model is, there's some resource that you want to protect, say some file F. And what you do, you draw a box around the resource in such a way that no outsider or no attacker can actually get to the resource. And that's the first starting plan, isolate everything. Then the second part of the plan is, of course, you do want to share occasionally, and so you want to enable sharing. And so the way you do that is, the basic plan is to have one hole in the wall, and through the front of the hole a guard. And all messages, all requests, that actually are for the resource are intercepted or inspected, or mediated, as it's typically called in security, by the guard. And so there might be a message, from the form like from Bob, and with the content, I want to read file F. And the job of the guard, is to look at this message, see who it's from, look at the policy, and then say yes or no. Right? And that's the top level sort of picture that we have. And this picture applies, the reason that we're sort of calling it out is it's a picture applies to many, many, many different types of computer systems. And it's a useful one to sort of have as an architectural picture in your head. Now, clearly, the role of the guard is important. And the guard has to answer the question, is this request that came maybe over the internet, over an untrusted network, is the request from Bob, really? Right? And that is really the question that user authentication tries to answer. Now, the guard has to establish that this message indeed originated with Bob and that he should apply Bob's security policy to it. Okay? So if we think about user authentication, it's helpful to distinguish 2 or 3 separate operations. One is registration. There's a common way, for Bob and the guard. So here somewhere is Bob. A common way, for Bob and the guard, to actually establish user authentication is to register for Bob some secret that he only knows, with the guard. Right? So that's the registration step that happens initially. Then the second step, the common operation, is the actual authentication. The authentication check. So in this simple picture, if Bob has some secret and has shared it with the guard in some previous step in the registration step, then the security or the authentication check is pretty straightforward. The secret can be sent along with the message, probably over an encrypted secure channel, arrives at the guard can actually see indeed does the request contain the secret, and if that secret indeed corresponds to Bob's secret, then the guard might actually conclude, well, this message must have been originated from Bob because Bob is the only one that could have known that secret. Right? That's sort of the base plan. Of course, there's all kinds of assumptions here immediately that are abundantly clear, correct? This assumes that Bob actually didn't share his secret with anybody else, or that the secret is not easily guessable, and we'll come back to that. Right? And then the third operation, which is the third operation is recovery. Let's say that Bob loses his secret or forgets his secret. There has to be some plan, for Bob to sort of recover his account. And this is typically sort of an Achilles heel of user authentication. And we saw a good example of that in the first lecture when Nikolai told you about this story where somebody tried to break in, to the account of a reporter by exploiting the recovery procedure of Google, the recovery procedure of Apple, and the recovery procedure of Amazon, and lined them up in a careful way to basically be able to reset, the recovered account of the reporter to point to himself. Right? And we'll see this show up a couple times in this lecture too, but it's always important to keep in mind that often here's where the crux is, what actually is the recovery procedure. Okay, so before diving into any of these 3 operations in a little bit more detail, there's a couple cross-cutting challenges that you should keep in mind. One challenge is something that's typically called intermediate principles. So principles is typically the term used for the entity that's being authenticated. And in this picture, I made it sort of very simple. I said, well, there's only basically one principal, and that's Bob. But that's really not true. Like in any computer system, it's not true, because it is not the case that basically there's a TCP connection out of Bob's brain going to the guard, correct? In fact, the way Bob actually interacts with the guard is he has a device that actually sends the request on behalf of Bob. And so that device you should be seen as an intermediate principal because it has to be trustworthy. If the device is not trustworthy, then when the guard receives the message from this particular device, with some secret, it won't be able to conclude that actually that the device is actually speaking on behalf of Bob, right? If the attacker has taken control over the device, then maybe the attacker is actually speaking on behalf of the message, correct? And so this is a very important thing to keep in mind, that often when in a particular security plan, the end user is one principle, but there's a bunch of intermediate principles that are actually going to affect the security plan. And the particular risk, there's so what are examples of these intermediate, your laptop, your phone, but maybe a load balancer. I mean, all the devices that are sitting sort of between the user and actually the guard that are important to actually the user authentication decision. And just to make it really clear why this is actually a real challenge that needs careful consideration, just think about a keylogger. Whatever, Bob, on his laptop, browses, maybe some shady websites. The shady websites happen to install some JavaScript on his computer that basically logs all his key presses. Right? A very, not uncommon attack. And so at this point, correct, the device is infiltrated with a bunch of malware, and every time when Bob presses a key, the malware can record actually what he presses. And so whenever time he types in the password, to log into an account, the attacker is going to have a copy of the password, right? And at that particular point in time, basically, that device, that intermediate principle, does not talk on behalf of Bob anymore, right? And so the security check will basically be meaningless. And sort of keyloggers are a real challenge in sort of any user verification plan. Okay. So a second challenge, or cross-cutting challenge, it's almost more an issue of perspective, is user identity. Often, when we think about the registration of, say, Bob at a particular website, the registration actually doesn't really establish user identity. Instead, registration identifies. Registration has often weak properties. So it's very well possible that when actually Bob logs in, sends his message, the guard checks the secret checks out, that the guard actually knows very little about Bob. And in fact, typically actually doesn't really know his identity at all. So for example, like if you create an account at Amazon, or if I create an account at Amazon, does Amazon know this is the real Franz Kashuk, that whatever works at MIT, lectures 858, et cetera? Does Amazon know it? No, absolutely not. Right? What do you provide when you register? An email address? Anything else? Well, presumably the most important part, correct, is when you buy something. So what do you provide when you buy something? Credit card. Is it important really to Amazon actually who owns that credit card? Probably not, correct? The only thing they want to care about is they can charge to the credit card and then ship off whatever goods you bought, right? And so if you think about it in terms of identity, correct, and when I log into Amazon, Amazon really doesn't know much about me. And that's actually perfectly fine, correct? I mean, in this particular case, they don't really need to know much about me at all. And so, and this is often the case, particularly with websites, correct? Where most of the websites, you first come, first serve. You create the account, and really the website has very little notion of who you are. For example, Amazon. So how could you do better? Well, if you log into Athena, and the server sees a request from your account, or I log into Athena, and the server sees a request from Kashuk, user ID, Kerberos ID Kashuk. In principle, does MIT or that server know quite a bit about me? Does it actually know my identity? What do you think? Yeah, go ahead.
So like if it was MIT that was like running the registration, they'd be able to like link it. But if it's just a third-party service and you put in your MIT email, then they wouldn't really know.
Yeah. So good. So this is a great example. So like, if you were talking to a true MIT service, presumably MIT is able to actually link you to that user ID to a true user, because you actually got when you registered at MIT or when actually applied to MIT, where there's an identity established, and from that you got your user ID, you got your Kerberos ID, and so it's directly linked, to actually who you are. But what's going on here, correct, is that the registration phase is much more complicated and much more careful than actually the registration phase that a website has, right? And so in those cases, one might be able to establish a true identity, or like when you're in a company and there's a system administrator that makes an account for you, right? And when you work for the company, you probably have to fill out all kinds of forms that really establish who you are, at least enough so that you can actually pay taxes. Okay, so MIT gives you probably stronger guarantees than actually in terms of the registration that, for example, Amazon does or Google does. How about a bank? Is this a first come, first serve, like websites, or is there sort of a stronger registration process? Yeah, go ahead.
Not to answer your question now, but just what we were talking about just a second ago, registration having weak identity. That feels like a feature, right? Like I want Amazon or Google to know as little about me as possible.
Yeah. Very good question. So like, there's a considerable sightline or an underlying theme here, which is privacy. Right? You'd probably be very unhappy to shop at a website that knew everything about you. And we'll see that coming up, throughout, this lecture. Back to, yeah, go ahead.
So presumably, if you have a bank account, then they like check your license and stuff, so they would have a strong.
Yeah, you probably, depends on what bank it exactly is and what kind of service you're asking for, correct? There are online banks where you don't really have to provide much, PayPal. But if you, whatever, go to Bank of America, you start an account, you presumably have to show a bunch of identities, and they create the account for you, correct, and give you the user ID that goes along with your account. And so there's a registration process that establishes a stronger identity than, so for example, Amazon or Google does, or sort of typical websites do. Okay? And so this is something just keep in mind, that, the fact, that the guard and the principal share some secret doesn't really establish the identity unless the registration process actually is a pretty strong registration process. Okay, so there turns out there's many ways to do user authentication. And in fact, we used to sign a survey paper in the past that we basically went over, had columns of text about like hundreds of different passwords or different authentication IDs that people have tried in the past, with check boxes about which one has this plus and this minus. And basically, the paper had one conclusion, which is that user passwords are actually pretty good. And so it's not so surprising that in some ways, most user authentication, or the most common user authentication process, is passwords. And so, the idea is pretty straightforward, correct? With register, basically, the user picks a password, bot picks a password, and gives it to the guard. And then the authentication check, is pretty straightforward. Then the guard basically checks the secret against the secret that actually was established during registration. And that's sort of your basic password scheme. And there's a number of reasons why passwords are there's one primary reason I think why passwords are so successful and so long-lasting, even though many other ideas have been proposed, is that because they're basically very user-friendly. you don't, passwords are just basically based on some secret, that you know and that I know hopefully nobody else knows. You have to keep nothing around. You just have to remember, that secret is in your head, and that's everything. That's all there is to passwords, basically. And you don't have to type them in. So it's hugely convenient in terms of usage, both, for actually websites and for users. One of the big downsides of passwords is they're incredibly valuable. And with that, I mean that if an attacker basically can guess somebody's password, he can impersonate that particular person, right? Or he can impersonate the victim. And so it doesn't require no break-ins, you don't have to write any malware. The only thing you have to do is guess somebody's password, and you're basically into a computer system. And so that makes passwords vulnerable or an attractive point of attack. And so a lot of the, if you think about the reading from Microsoft that we just assigned today, correct? That was all about talking about the possible attacks that people actually launch, and they all launch them on the passwords because it is just like an easy point. It's a very vulnerable point. In addition, it's sort of made worse is that there's a human factor here. Namely, users typically pick passwords that are easy to remember. As opposed to like, a password that is 20 characters long, correct? Which is going to be hard to break, as was a discussion in the Microsoft document. But it's very unfriendly for users and probably can't actually remember 20 characters. Furthermore, there's a tendency to share the password across sites, across services. Because then you only have to remember one password instead of many. And it just makes your life easier. And what is interesting is that because passwords are so common and have been so common for years, people actually have studied them quite carefully. So there's a whole literature on how users pick passwords, what are good password policies, should you have restrictions, rules like, you should have, characters, numbers, capital characters, none, characters in your password, all that kind of stuff. But probably most interesting is first to look at some basic statistics. So here's some statistics from 2009 and 2010, mostly 2009, and basically it lists the top 20 passwords. And so this is data collected from a break-in. Somebody broke into some website, stole the whole password file. The passwords were not encrypted, and you can just look at it, and people got because people broke, they shared it, and so this information is available, and we can study them, right? And so as you can see, the top 20 passwords are not so surprising. The number one is 123456, a really secure password. But what's more interesting is that if you look at this whole data set, which has about 6.4 million users, there are 5,000 unique passwords that cover 20% of all the users. Right, so that means that you cannot allow an attacker to guess 5,000 times, because then there's basically 20% chance that he has actually he's broken that particular account, correct? Furthermore, some passwords are just shared widely. 123456 is used by lots and lots of different accounts. So if an attacker just tries 123456 on all possible accounts, then he's likely to get some account, right? And again, so if you're on the defensive side, you probably sort of have to make sure that you forbid somebody to basically try every user account, correct? This turns out this is like one particular password file. People have done studies with many, many, many different password files. There's a similar study for 2010 when there was a Gawker break-in, if anybody remembers the Gawker website. And it has similar sort of type numbers. So this is like, users really do pick weak passwords because they're easy to remember, and users do share passwords across sites. Right? And so this is a real challenge if you're on the defensive side and need to deal with this. So what do you do? So what are the defenses? Basically, there's a sort of a central theme for all the defenses, and that is basically rely on passwords as little as possible. And that is sort of an obvious high-level strategy, but it has its manifestations in multiple different ways. So one example of this is typically you use a password only once at user authentication. So typically what happens, you use it once per session. You log into some particular website using your password, and do part of the the login process, a new secret is established, and that secret is used for the rest of the communication with the website. So the password is only used once, and from then on something else is used. Typically in websites, correct, the website will give you back a cookie. The cookie will be stored in the browser, and the cookie will be then used in future requests to actually authenticate you. Right? Now that's a good example of that. Yeah.
Isn't there like a trade-off though that if you get users to use the password more often, they're more likely to remember it? Is there really that much of a security benefit from having them enter the password less? If your cookie or whatever is always still ultimately reliant on the password, doesn't matter how many times you use it.
I think in general, there's good security philosophy to sort of corner off the password as much as possible and don't expose it, and rely on better secrets than the password for subsequent authentication. So coming back to the user, so the next, so these are there's multiple parts to this strategy, and another good example of this strategy is to actually use a password manager. And the idea in a password manager is you pick some password manager. It actually stores all your passwords, and it picks passwords for you, or suggests passwords for you for a particular, for any site you want a password for. And it can suggest very strong passwords, because it will fill it in the password field when actually you need to use it. And similarly, it can actually ensure that actually every password you pick is unique per site, and so you don't share your password across many sites. Right? And basically what this reduces, of course you have to log into the password manager, but you do that once, in the beginning of a session, use that one password that you do have to remember. Hopefully you can pick a really good one for your password manager, but that's then the only password you really have to remember. And this is why you see, almost in every company or everywhere you go, please use password managers. Please use password managers, for user authentication. Right? Who here uses a password manager? That's not that many. So maybe you guys have even better plans for security than password manager. That's certainly one part of the plan. Right? Or maybe this lecture will convince you that maybe it's about time to start using a password manager. The other reason to corner the passwords into just user authentication is that actually then it becomes possible to rate limit their use. And you'll see that in a little while. That's extremely important. Since you see that from these statistics. If an attacker can actually guess passwords very quickly, for example, try 5,000 passwords very, very quickly, it's likely that the attacker is going to succeed. So we want to make it possible to actually slow down the attacks or slow down password guessing by quite a bit. Of course, it still has to be interactive. Like when a valid user logs in, and types in the password, it shouldn't take an hour to come back and say oh yeah, your password is correct. It should be milliseconds, time range, correct? But it can be much faster, much slower than instantaneously. And we'll see that as a good defense. And then the final thing, which we're going to talk about, is to use augment passwords with a second factor. And there can be different types of factors. One way to think about this is that a password is something unique that a user knows. But you could have other factors, like the secret could be based on something unique that the user has. For example, public key, crypto key. Or it could be something unique that the user is, whether some biometric, form of authentication that can augment, the password authentication. We'll talk a lot more about this in a little while. So, but those are sort of the prime defenses against or to strengthen, the use of passwords. Okay, I'm going to talk a little bit about passwords more in detail, like and how to store them and things like that, and then I'll come back, to the second two-factor authentication. Any questions so far? Yeah, go ahead.
See how using a password once per session increases security of the passwords, besides like decreasing the frequency that manual attacks could occur.
So that's one aspect. The second aspect is that immediately you swap it for a much stronger secret once you're sort of logged in. And that stronger secret, then protects your communication. So there's initially a weak secret, and then boom, you switch immediately to a strong secret.
But like if someone has the password, doesn't matter that you
So the password is lost at that point.
what's the point of having a strong
Because you want to expose the password as little as possible. And you have a few operations as possible to rely on the strongness of the password. Any other questions? It's a great question, by the way. Yeah, go ahead.
Maybe just a comment. So do you think that actually simple passwords are really a problem? Because if I remember, all these leaks were coming from websites like Adobe or some random forums where people are just annoying to create an account and just use maybe one time like random passwords, but they might use different passwords for much more important things.
Yeah, very good observation. It's true, like, for a website you don't really care about, you probably pick you don't care too much about the password either, correct? For websites you do care about, it's still hard to do a good job, correct, against a determined attacker who wants to guess your password. And you saw that in the reading from Microsoft, correct? What is the length of the password that is recommended if you wanted to have some chance of surviving? Anyone remember from the reading? Yeah.
Somewhere around 12.
Somewhere around 12 characters. How many people here in the room have a 12+ character password? Pretty good. Excellent. All the others probably need to improve the password. So it's not that straightforward, right? So I think even with even if you care about the account, you probably there are quite a number of weak passwords out there, and which is why the second two-factor authentication is so popular. Okay, so a couple things that basically are particularly relevant to Lab 2, where you will be playing with a little website, and it has a brain-dead password plan that you have to improve. And so in Lab 2, as I handed out, Lab 2 uses a really bad plan for storing passwords at the server. And the basic plan that it uses, there's a table with user ID, and then password. And so you have user 1, and it stores in plain text the password 1, 2, 3, 4, 5, 6. That clearly is an incredibly bad plan, because if ever the server gets compromised, correct, and the attacker gets hold of the password file, then it has the password for all user accounts. And if a user uses the same password at multiple sites, you might actually be able to break into other sites too. And so this is not a great plan. And so nobody does that really in practice, or nobody should do that in practice. And typically, what people do is actually they exploit or use something that's called a cryptographic hash function. So this is one of the cryptography or crypto functions that we're going to be using. Cryptographic hash function, sometimes called one-way functions. And they have this great property that you can take a message and hash it to some shorter digest. So for example, you can take a long message, an 8-byte message, something, and then digest it to something 128, 256, byte digest. And the property that the one-way function has is that if you get a hold of the digest, it is computationally very difficult to compute what the M was that actually resulted in that digest. We're not going to talk much in this class about actually how to implement these cryptographic primitives. We're just going to assume they're there and basically outsource all the implementation of cryptographic functions to 6857. So if you're very interested in that, you should definitely take 6857. Probably a number of you actually are taking it in parallel with 6858. How many people are in 6857? Okay, quite a few, not that many. But the main thing just to remember is it has this great property that if the attacker has the digest, it's hard for the attacker to actually figure out what the input was. It's computationally very hard. And so instead of storing the 1, 3, 4, 5, 6, what we're going to be doing is you're going to modify the lab code to actually store the cryptographic hash of the password. Right, and so this changes user authentication a little bit. So the basic sketch now for user authentication is as follows. When the user logs in, sends in the request, the password, the site computes the hash of the password when it receives the password from the user and compares the hashed version of the password with the hashed version that actually is stored in the table. And if they match, we know for sure that basically that must have been the same M that was the original input, and therefore this is actually the actual user. And this is the great advantage, correct? That if an attacker steals the password file, not all the passwords are just there in plain text. Okay. Now, this is typically not good enough yet, and so people are more sophisticated than this because this is vulnerable to a rainbow attack. Basically, what the attacker can do, and based on the statistic that you saw a little while ago, correct, is just compute ahead of time a table, with all hashes, of common words. Take the 5,000 popular passwords, compute all the cryptographic hashes in advance, steal a password file, check the hashes against the ones that you pre-computed to the ones that actually show up in the password table, and you know what the inputs are, right? So typically people make it a little bit stronger than this, and one way to make it stronger is to actually what's called salt all the passwords. So instead of actually storing just the password, there's a second column. So let me erase this. We're going to store a user ID. We're going to store a salt, which is just a random number. And in the password column, we're going to actually store, I'm going to erase this a little bit. We're going to store the hash of the password concatenated with the salt. So what does this do? So yeah, go ahead. Yeah, if two different users have 1, 2, 3, 4, 5, 6 as a password, they're going to have two different salts. And so hashing or concatenating the password with the salt is going to result in a different hash, correct? And so even if the attacker pre-computes a table with all the hashes of common words, it's not going to work. Instead, what the attacker has to do, correct, is compute that table for every user independently. And it becomes suddenly a lot more expensive. Furthermore, you don't want to use any cryptographic hash function. You want to use particular types of cryptographic hash functions, because if you can make the computation of a cryptographic hash function slow, right, it will take a long time for the attacker to basically pull off this attack. Right? And so the second part of the story is that actually you want to use an expensive hash function. in fact, there are hash functions, totally designed, for this particular purpose. If you're interested, Google bcrypt or some of the other ones. And so these are hash functions that have the property. They're still cryptographic hash functions, so one-way functions, but they're expensive to compute. They take many, many, many cycles. Anybody remember actually what Microsoft did in that white paper that we read for today? How did they make it more expensive?
Repeat like 1,000 times.
Yeah, I repeated one of the SHA-256, I think it was, 1,000 times, correct? Just to make it a little bit more expensive. And since, recomputing the SHA over, you can't parallelize it, correct? And so, it's going to be 1,000 times, a SHA-256. And again, this is exactly for this particular purpose. Yeah, question?
Are there ways to come up with algorithmic shortcuts to see, like, if I compose the hash function multiple times, like maybe it's a different hash function that I can get?
Very good question. And so this gets us back into, and this is all the questions you want you to ask, correct? Of like any crypto primitive that's given to you. And the basic answer in the 658 is, we're relying on the mathematicians to do a good job of actually designing the cryptographic hash functions. But this is something definitely worth thinking about. And in fact, this is one reason why you should never, never, never design your own crypto functions. Because you're most likely going to get it wrong, and you're going to have some subtle issue like that where there is actually some non-composability in the primitive that you thought was not there, is there, and actually breaks it. Right? And this is also one reason that we spend almost no time on cryptographic functions in general, because we're going to assume there's some interface that has some properties, there's some API with some properties that's delivered by the cryptographic hash functions. And implementing those cryptographic hash functions correctly is difficult and challenging. And so that's all in 6857. Yeah?
So if an attacker has access to the password list in this database, they would also have to solve. They can't just spin up like 100 VMs and run the most common passwords against everyone's solve.
Yep. And it's exactly what the Microsoft paper described, correct? Basically there's and at that point there's just like nothing you can do. So first of all, you hope that the password file doesn't get stolen. And so, I'm sure Microsoft Azure spends a lot of time and energy to make absolutely sure that, it's very difficult for anybody to steal their password files. But even if it's stolen, it will take some time, for the attacker to crack. But yeah. Actually, the number in the paper was truly impressive. Like, how many passwords could they do per second? Anybody remember the number? Yeah, 1 billion, correct? Almost in that order of magnitude. So if you really care and you want to attack somebody, and you have the money to buy a rig like that, as described in the paper or in the white paper, passwords is not very strong. Unless you have a 12-character password, correct? And then, you'll be in good shape. Yeah.
You said the salt is a random number.
Yeah.
So can you say more about that? Like how?
So we're going to just come back maybe to the first lecture that we talked a little bit about early on. It's first important, that very important, that it's a good random number, right? And that it is actually really, truly a random number generator. Often this turns out to be a problem in practice for people to generate good random numbers. And so there's a bunch of functions. Nikolai mentioned them a little bit in the first lecture, where there are functions designed called pseudo-random number generators. This is another cryptographic primitive that you give it some seed. It does a great job of generating a pseudo-random string that really looks to be random, assuming that you put in a really random seed. And so in practice, people spend quite a bit of time to generate this random seed, and then use a standard off-the-shelf pseudo-random generator to actually generate these salts. And you will see that a little bit in lab 2. You will have to do this. Yeah, or at least you have to use it. Yeah.
Could you just use like 1, 2, 3, 4 as salt, and still the hash function will just map it to something?
Yeah, except if somebody, an attacker, also guesses 1, 2, 3, 4 as your seed, then he can reproduce the same random numbers. So it is important that you don't do that. Any further questions? Does it all make sense? Okay, so far this is all pretty, presumably a lot of things you're already familiar with. So let's talk a little bit more about two-factor authentication. And that's sort of basically the biggest change I would say in the last 5 years in terms of user authentication. So as I said before, so password is a one factor, that sort of represents something unique that the user knows. But you could exploit other factors or augment that with other factors. And so that's what almost these days, like any security sort of white paper you read, it basically says like please sprinkle two-factor authentication on top of passwords, and that will improve your security dramatically. And what does it do? There's two things that it helps with. Defense against weak passwords, because it's only going to be one of the two factors that's actually going to go into the user authentication decision. So even if you had a weak password, but you have a strong second factor, then hopefully the strong second factor will actually protect you. And it typically is also good against phishing attacks, or helps with phishing attacks. The idea being that you maybe type in one factor through one particular interface and a second factor through another interface, and so the attacker has to phish both interfaces to actually be able to get your two factors, and that makes it more difficult and more challenging. Not impossible, but more challenging. So those are the two sort of attractive properties that get people very excited about two-factor authentication. And there are all kinds of different ways of doing two-factor authentication. Many of them you're probably actually pretty familiar with. We use some of them here at MIT, correct? So one approach is a code through an SMS. And so the basic plan is, you've seen this, how many people have seen this before? I presume everybody has, yeah, right? The idea is pretty straightforward. You log into your, you want to log into your website. The website has your phone number registered, and before it actually allows the login, it will text you a number and some code that you need to type into the web page. You type in the code in the web page, and if the password checks out and the code checks out, you're logged in. And this is a very common way for websites to use some form of two-factor authentication. How good is that form of how good is this approach for two-factor authentication? Is it easily hackable? Does anybody know? Yeah.
It's better because now the attacker needs to either have access to your phone or to like the network carrier.
Yeah. Okay. So first of all, no matter what is going to come out of this discussion, it is better than having no second factor. But let's say, is this good against a targeted attack? Is the attacker likely to figure out what my phone number is? Probably, right? I mean, it's not a really true secret. So it's probably likely that the attacker is able to find the phone number if he really attacks a particular user, correct? So once you have a people's phone number, is it really a phone number tied to your phone very strongly? What do people think? Yeah, go ahead.
You can social engineer your way into somebody's phone account and then just listen, get their and use the card.
Yeah. So this whole approach, as you point out, is actually very susceptible to social engineering attacks, where you call up the phone company and say like, I'm a Franz Kashuk, I just want to change a little thing in my account. I would like to forward my phone number also to this other phone number, and so that all text messages arrive in both places. All right, and so attacker can presumably make this happen if they care a lot, and then basically receive then the attacker, correct, job is pretty straightforward. You log in, or the attacker tries to log in as you, the text message is being set, the text message is being forwarded to the phone number that the attacker controls. The attacker sees the the code and can then log in as you, right? It's also very susceptible to man-in-the-middle attacks, right? Where the attacker puts a web page up saying like, hey, this web page looks exactly like, say, your bank.com is the trusted website that the user wants to go to. The attacker sets up a website, secure.bank.com, that looks exactly like bank.com, tricks, the user to visit, userbank.com, thinks, hope, that the user thinks that this is the real, bank.com, even though it is not, correct? Puts up a login page, user types in the password. If the attacker knows, that the user actually uses an SMS, the attacker says, okay, please type in the code, right? And delegates the request to the real website. The real website will ask the user's phone to actually type in the code. The user will type in the code in securebank.com, the attacker's fake website, and boom, the attacker can forward that code back to the original website and is in, right? So it's actually it's not, it's better than to some degree to phishing attacks, but it certainly doesn't stop, phishing attacks. Does it make sense? So in some ways, what it does, correct, it pulls in the whole phone network into your trusted computing base. And the security of the second factor relies on the security of actually, the phone infrastructure. All right, so hugely popular because for one reason, it's extremely easy to deploy, and it does buy, something in practice. A second common approach is time-based, one-time passwords. They're not like user passwords that are user passwords as the ones when you set up your account, but there's like tokens or numbers basically. And for example, a common example use case of this is like Duo. How many people use Duo to log into the MIT VPN? Good. So that uses this particular scheme, and the scheme is pretty straightforward. Basically you have to install an app on your phone like Duo. Duo, the app, and the server register or share a secret. And so when you install that app on your phone, a secret is actually installed on your phone. And when you log in, and when it's asked for approval, the app computes that the secret, takes the secret, concatenates the time, and hashes that, and sends the result of the hash to the surface. And so that's then your second factor. Right? So how good is this scheme? Is it better than SMS? A number of people say yes. Why?
Yeah, it's still one of those man in the middle things, but somebody else can't social engineer your phone carrier into
Yeah, the social engineering attack is probably quite a bit harder to pull off, correct? Does that make sense? You're saying it's probably still phishable. Why is that the case?
because I don't know, like someone with a good modern phishing framework can just ask you for your one-time thing, right, and relay it back to the...
Yeah, the attacker sits basically between all communication between you and the website you're trying to log into, correct? He can, record, that one-time thing coming from the real website and from your phone and play it back to the real website, right? So it still has this, yeah.
This protocol is only 6 characters, 6 numbers.
Yeah, so some of the protocols don't tend to be that strong. That's another issue. What is another issue? What happens if the server is compromised? Is that a dramatic event or is that a small event? What needs to change if the server is compromised? All the secrets have to be changed, correct? Which would mean that basically all your Duo apps probably have to be either reinstalled or actually downloaded in some way and get a new secret, correct? Another downside in terms of usability, often is quoted is that, if you switch phones, you have to install the app again, correct, and register a new secret, with the site. So, it's just not as portable as some other, not as portable as passwords, correct, which you could go from one computer to another computer and boom, it just works. Make sense? But popular, and, actually is an improvement over one, and it is definitely an improvement over not having a second factor at all. Yeah, go ahead.
Of concatenating the time, if I'm trying to guess that secret, so I'm just brute forcing the secret string, don't I just append whatever the current time is, plus or minus the second or something, and then send those?
Hold this thought for a second, and when we talk about replay attacks, that would be a good thing to talk about. Right? Like the real issue here is if you didn't have the time, the attacker at some point a year ago recorded that message, then you could just replay it and it would be still working. And so sticking the time in makes it more unique. That's the basic. This is a replay attack.
Okay, so it's not that it makes it easier to guess or harder to guess. It's
It's also harder to
if
guess,
it
but I think the primary use is replay.
Okay.
Okay, good. So the third approach, which is the topic of the second reading that we signed for today, is UTF. And so, and that is a strictly stronger, than the two other approaches that we have described so far, or talked about so far, and it gives you stronger, security properties. And so how many people use a UTF device? Anybody uses that? One? A small number, correct? If you're really curious about them, you can actually, MIT offers them for free to students. And so they look like this. This is like a UTF device. Just so the USB, you stick it in your USB slot. When you log into a website, so I use it for Google for my Gmail address. When I log in from a new browser into Gmail, Gmail will ask me first for my password, and I'll type in my password, and then they say please, stick your YubiKey into the USB slot and press the button. It has a button here, and then it presses the button, and Google and my UTF key chat a little bit, and then it will say, yep, this is indeed the key that you have registered with your Gmail account, and so we believe that this is indeed Franz Kaschuk, and so you can log in. All right? So that's sort of the basic use case. And it relies on, at a very fundamental level, on public key cryptography. And so this is yet another crypto primitive that we're going to be using in this class. Public key crypto. And the basic idea or the basic property that public key crypto has is that there are two keys. So compared to secret key cryptography, in public key cryptography, there are two keys. One is typically called the private key or the secret key, and the other one is called the public key. And the idea is that the private key you should keep private and not disclose to anybody, but you don't have to give it to the receiving end. The receiving end gets the public key that everybody can know, and can then use that public key to actually authenticate the messages actually came and were signed by the private key. For example, one of the problems that I've talked about here so far, in particular the problem with passwords, is correct that both the service and Bob have the copy of the password. All right? And so in principle, the servers could impersonate Bob to other services, correct, if we're using the same password there. And with public key crypto, basically the plan is that Bob is going to have the private key, and he's the only one that's going to have the private key, and the service is only going to have the public key. Correct? And in fact, in this particular device, there's something in here in this. This is manufactured by YubiKey. There's a little what's called a secure element inside of it, and that secure element stores the private key. Like a 1000-bit or whatever, 1024-bit, secure storage that actually contains the private key. And that private key is unique. You know, it's like my private key. There's hopefully no other private key that has the same set of bits in it. All right? And so this can be used in various ways, but in the way that's used in UTF is as follows. There's a signing primitive. So there's a sign call that takes the private key as an argument. It takes some message M, and then it produces a signature. It's just a sequence of bytes. And then there's a corresponding operation, or that primitive that actually is on the server side. That's called verify. That takes the public key as an argument, the same message M, and the signature that may be received over the internet, and it basically says OK or not. And if it has OK, that means that M was actually the message that was signed by the originator. If it was not OK, then basically the signature doesn't check out for the message that actually was being received. And that's sort of the building block, you know, for this UTF protocol. You know, the basic idea is going to be, you know, Bob is going to sign, you know, some message, or the YuBi key is going to sign some message with the private key, and, you know, include in there whatever I want to log in, you know, send it over to the server, and the server then will take that same message, recompute it, and check whether the signature actually matches, and then we know for sure, you know, that actually that message came originally from Bob. Okay, or signed with that particular private key. Does that make sense? That's the basic building block. So just these two cryptographic primitives, again, we're not going to talk about in this class about how you implement them. You know, that again is a topic, you know, for another class. But you have to use them with care. You know, you're not done, you know, by just having this primitive available. You need a larger protocol to actually protect against particular attacks. And so the UTF protocol basically uses these primitives to implement you know, secure user authentication between, you know, a user and a site. And so I'm going to go through the protocol in a couple smaller steps, so to explain, you know, what each piece of the protocol does. So the base protocol, where it's like the first part of the protocol, I'm going to describe this using timelines. So we have a timeline. Here's the server. There's a browser, the browser principal, and then there's the device, like this, the little blue device that you just showed you. That's the third principal. And, you know, the basic protocol is as follows. You know, at some point, you know, I want to log into, say, google.com. You know, I send in a login message or basically the browser runs some JavaScript that was produced by Google, and I click on login. You know, the login sends some information to the server, and the server, in the UTF protocol case, responds with a challenge. C, and which is typically, you know, this is what it. And this is typically just a big random number, a fresh picked random number on the server side. The browser sends that, you know, communicates with the UTF, you know, token all across the USB channel, correct? So I plug it into my computer in the UTF slot, in the USB slot, and the browser basically talks directly to my device. And so this UTF device and the secure element you can think about is a very primitive, simple processor that sits inside of it. You know, probably simpler than the beta that you saw in 004. And so something simple, truly simple. And basically, the browser forwards the challenge to the device, and the device signs with the challenge with the private key. So here's the key private. C, and that produces a signature S, correct? And basically, the device gives that S back, you know, to the browser. The browser sends S, you know, to the server. The server has the corresponding public key, and basically, you know, knows what, you know, C is, correct, because it sent it in, so it can compute, you know, verify kpub C signature. And it is going to say true or false, correct? And if it says true, what do we know? Yeah.
The user that we're talking to has that key that we were requesting because they like signed the
Yeah.
number.
We know that, for sure that the device actually signed, that challenge with its particular private key for the user that we're expecting to be signed in for it, correct? And so we're going to have high confidence that actually this is, the user that we intending to log in, all right? If it says false, what does that mean? So when does the primitive say false?
When it was signed by a different key, or
Yeah, it was signed by a different key, correct? Or if, C is actually not the C that was actually signed. Like say maybe an attacker, recorded an old C from a little while ago, right? And they replayed that C from a little while ago. That would be different than the C that the server is actually using at this point in time. And so then the primitive will say, nope, that's not a correct C because, that was not the C that was signed by the YubiKey, correct? So what does the C protect against? Yeah, replay attacks, right? So that when the attacker records some C and tries to replay it later, it won't work because the server is expecting something different. Okay, so this deals with replay attacks. That's one simple attack. The more bigger challenge, as we'll see in a second, is, again, man-in-the-middle attacks. And this is the typical thing with user authentication. It's always man-in-the-middle that is the challenge, correct? Somebody that sits, the attacker that sits between the user and the Destiny website. So let's look at that for a second and just see first why this protocol is not good enough if we have a man-in-the-middle attack, and then we'll see what actually UTF does to make it stronger. So men in the middle are so common that it has an acronym. So the basic idea, plan, from the attacker's point of view is as follows. We still have ours. So here we have S, say bank.com, like the website that we want to log into and do an actual secure transaction. And basically, the setup is as follows. The attacker sets up S prime, say securebank.com, and which looks identical to bank.com. And so if you visit the two websites, you can't tell the difference basically from them. And basically the plan is for the attacker to trick the user into actually visiting S prime, believing that actually the user is talking to S, right? And so let's say the bank or the attacker succeeds. So here we have our browser, we still have our device, and so the bank or the browser sends a logging request to S prime, right, believing that actually it's talking to S. What the attacker does, it actually forwards the logging request to S. S picks a challenge, C. The attacker gets the challenge, forwards it to the browser. So the browser logs in, correct, and just now sees like, oh, google.com. Google.com is asking for a signed signature on this particular challenge. The browser sends it to the device. The device produces the signature, correct, for this challenge. The browser responds to or sends it to the service, S. And then what the attacker does, it just relays that same request or that same challenge, the signature, to the service. And what will happen here? What will happen at the verify step? Will the verify check out? Yeah, we'll respond true, right? Because the verify function is going to take that secret C that was actually generated by the server, uses the private key that corresponds to the corresponding public key, and the signature will check out because it actually was signed with the private key and with the value C, right? Does that make sense? So this protocol is not good enough, correct? Because there needs to be more mechanism in the protocol to ensure that these man-in-the-middle attacks are difficult to do. And so basically, the plan is reasonable, actually straightforward. In addition to, so when we're going to modify the protocol slightly. Let me browse, put it on here. In addition to the challenge, we're going to provide some additional information. So we're going to send C to the browser, or the browser sends C to the browser, but it also sends the origin. And what is the origin? Well, the origin is the domain name or the URI or the URL for the particular website that we're logging into. So let's assume for a second that this is we're logging into securebank.com, so the website run by the attacker. Right? So in this particular scenario, we're logging in. The attacker has confused us and has set up a website that looks exactly like bank.com, but it's called actually securebank.com. And that is actually what shows up in the top of the browser window, right? Because like when you set up a TLS section, and the whole protocol assumes that you're talking with HTTPS, to the server, and so the browser will display like a nice green bar, because presumably the attacker did a good job and got a certificate for secure.bank.com, and so the browser displays secure.bank.com with a green lock next to it. Maybe the user didn't notice that it's a securebank.com instead of bank.com, or maybe it's thinking, well, it's probably still bank.com. Or whatever, but the user is, believing that it actually is the website, that actually is logging into, as opposed to the one that's controlled by the attacker. And so what the browser now will do, in addition to sending C, it will send C plus the origin. So what is the origin in this case? When the browser, so the browser talks to S prime, and it will communicate, for the C plus, the browser will pick up the name out of the browser window for whatever is talking to using this TLS connection, correct? And that's going to be S prime, because that's what it's actually talking to, and it got a certificate for S prime. So it sends C plus S prime to the device. The device, basically concatenates the two and signs that and produces that as a signature. The signature goes back, to the server. The server recomputes, basically runs the verify function, correct? And in principle, actually, the server sends a bunch more stuff back. It sends back it actually sends back what it signed. So it sends back actually C and S prime. Unfortunate name, so this is a signature, so let me call that SIG. C plus S prime, this is the SIG, plus C plus S prime, and SIG and C and S prime. And so the server, takes whatever these pieces of information that it got back from the device, checks the public key for the corresponding user, recomputes a signature, and the signature will check out. So that will mean that the device, my YubiKey, signed C plus S prime. But then this website does one more check. It actually checks whether the origin that came back and was signed is actually its origin. And it will find out, correct, that S prime is not equal to S, and therefore reject this logging attempt because it's a man-in-the-middle attempt. Does that make sense? Yeah.
For S prime to trick the browser to sending S to the
So here's an important part of the UTF protocol. A lot of people ask about this. In this story, the browser is trusted. So it is assumed that the client that runs the browser is not compromised. And that's an important part of the security story. If the machine is actually compromised, and you can easily see why this is true, let's say the client is compromised, and the attacker controls the client in addition to S prime. What can the attacker do? You can ask the device, correct, to sign anything it wants. You can pick, the C, you can pick the S prime, and just like, oh, please sign this, please sign this, please sign this, and relay those back, right? Okay, good. So there's one more tweak to the protocol. Let me briefly mention that. So in this scenario that I just described, basically the origin was different, correct? The attacker did not have the same origin. So one attack that could be one step up from this is that the attacker is able to get the certificate for bank.com. So maybe, and we'll talk a lot later about how you might be able to do that. This turns out to be, okay, we'll talk a little later about how to do that, but it can happen, where an attacker is actually able to basically ask a CA for a certificate for a website that it actually doesn't know. Of course, that shouldn't happen, but there are cases that it happened in the past. And so in that particular case, the attacker is not S prime, but it basically is S, right? Because then the TLS connection, HTTP connection from the browser to the S is set up, or to whatever to some machine that the TLS connection is set up to some machine that the attacker controls. The attacker has the right certificate, so it sends it back to the browser. The browser will display in a green nice box, yeah, this is bank.com, and then it will send bank.com, which is S, to the device, and everything will be good, correct? From the attacker's point of view, because it will be approved, and S also will see, this is bank.com, that's me, right? So that would be successful. So if the attacker can control or has a certificate or can produce the certificate for a TLS connection, we're still not good enough, right? Does that make sense? So there's one in addition. In addition to the domain name, we sent the challenge plus the duration plus something what's called the TLS channel ID. What is the TLS channel ID? The TLS channel ID basically uniquely identifies the TLS connection. So in this picture, how many TLS connections are there? 2, correct? There's one from the browser to this particular server, S prime or S, and then there's a second TLS connection that the attacker set up to the original website, correct? So there are 2 different TLS connections. And so these 2 TLS connections have different channel IDs. And so when the browser forwards C plus S plus the origin, it will also send along the channel ID. That will be signed. The channel ID will be sent along with all this information back to the server. And the server, checks the signature. Signature will check out. We'll check the host name or the origin. We'll check out if we're assuming that the attacker has the certificate. And then it checks the channel ID, and the channel ID will not check out, right? Because this is the second TLS section and not the first one. Does that make sense? So this is why all these 3 pieces of information are here to defend against these 2 attacks. Okay, so how good is this device and this protocol? And one way to think about this is to sort of think about other kinds of attacks that one might be able to pull off. So other attacks. And we already talked about one of them. Attacker compromises the client. And that's a problem. The protocol doesn't really handle that really well. What are the other problems that you can imagine? Is this the only possible? Yeah, go ahead. Steal the device. Yeah, steal my device, correct? Like maybe I'll leave it here on the table, and you grab it after lecture, and then you can log into google.com as me, right? So steal the device, you lose the device. So steals the device. How bad is that? Pretty bad, huh? So what is the solution to this? Yeah.
First, you still need the password. So the moment you realize the device is stolen, you can just cancel that device in your services. But you can also solve it with biometrics, for example.
Yeah, so basically this comes back to like the first point of this lecture, or one of the early points I made in the lecture, correct? There are 3 steps in 3 important operations in user authentication. Register, authenticate, and recovery. And so this is a recovery problem, correct? And every website has its own set of policies, and as we saw in the first lecture, they may interact wrong. So what does Google recommend? There's a bunch of different things you could do. One thing you could do is have 2 UTF keys. One that you store in a drawer at home, correct? And so when you get broken into or you lose one of the UTF keys, you can use your second one to log into the website and reset and basically cancel the other one and remove the other one from your account. There's a bunch of other backup plans that Google has. Some that are stronger than others. Like having a second one is a pretty strong backup plan. Does that make sense? Okay. Okay. One important point I wanted to make before I forget: if the attacker compromises C, the client, correct, or the browser and the client, that is pretty bad because it can feed any information to the device, and the device will sign it. There's still one very good aspect to it. So, for example, let's say the UTF protocol was implemented in software. Where would the private key be stored if it was completely implemented in software? And I run the application, say, on my phone. Yeah, it would be in the RAM of my phone. And presumably, if the attacker controls my phone, correct, then presumably it can also steal the private key. In this case, can the attacker steal the private key? Not, correct? Because it's still sitting on my UTF device. So there's still a real benefit, against attackers that compromise machines. Okay, what is another possible attack? Actually, one that actually is mentioned in the document. It's the final one that we'll discuss today. So how do you get the UTF key?
Compromised device by an attacker.
Yeah, maybe the attacker actually manufactured your UTF key, and you got the UTF key from the attacker. And the attacker actually has the private key that sits in your UTF key. And so there's an issue of like, where's the actually, there's a supply chain attack. Where does the actual device come from? And what's the story of that? What is the answer? Or what is the proposed answer?
Manufacturer key, so the device can prove that it's
Yeah, so
made by the right.
there's something what they're called in the paper, in the document, called an attestation key. And so the idea is that the device actually has burned into some additional keys that you can use to verify that this actually was a key that came from Ubicom and was manufactured by Ubicom, and therefore you should have some confidence that it actually is a trustworthy device. Does that make sense? And so this protocol has a bunch of other protocols that actually for secure attestation to check whether the device or the server can ask the device to actually attest to itself and by whom it was made. Okay? Okay, so this was a quick introduction to user authentication. As you can see, it's a challenging topic, but crucial, and basically any lecture that we do from here on assumes some strong form of user authentication. See you on Wednesday.